and he has also qualified NET CSIR exam. And he's a physics teacher with an extensive 26 plus year experience after completing his PG postgraduate from IIT Roorkee. He has research experience from IIT Delhi and Hong Kong University of Science and Technology. He has published 40 plus apps on Google Play Store, and he's an author of 18 books. He's an evangelist for MIT App Inventor 2 Scratch, blog-based coding and use of AI in education, author of 10 plus HTML JavaScript simulations. He's an author of anytimeteacher.com, which is a free portal for physics, and a winner of Rockstar Teaching Award, Visionary Teacher Award, Acharya Devo Bhav Award, and School Leader of the Year Award. He is a Life Empowerment Award. He has also obtained Life Empowerment Award and Dr. S. Radhakrishnan Memorial National Teachers Award and other awards and recognitions. He's a second prize winner of national competition in computational physics and a speaker at various conferences and workshops, and as well as resource person under also including under Professor H.C. Verma and IAPT. We welcome such an inspiring educator. And today I take this pleasure in inviting Dr. Tyagi for today's much awaited talk on quantum algorithms. Over to you, Dr. Tyagi.
Thank you so much, ma'am. This is the ninth session in this special program, special drive that IAPT has initiated. And I'm very much honored and very much pleased to be associated with this program. So this session 9, tomorrow we'll have a closing session, summarizing session. So technically this is the last talk about the content on quantum computing. And through this program, IAPT has been, has envisioned to reach out to school students. Something which impressed me a lot, because quantum is very, very weird at school level. It's even more weird. So this session is on quantum algorithms. And one algorithm that we are going to talk about has a very tough name, especially for people like me. Now, how do you read this? So you start reading it douche, even if you are able to put T silent, douche, josa. By the way, it's Deutsch. So, but then you read it douche, josa, and I had to take this name so many times this evening that I have a way out. One way out is a non-offending way of easy, say, making it easy to take the name. And that is, I take the first initial and I call it DJ algorithm. So it's easy to call DJ algorithm. The second one, which might offend some, but I request you to take it playfully. Replace a D with J and J with D, and you have a juice dosa algorithm. So whichever you like. Jokes apart, in brief, the session today will talk about the problem statement of this DJ algorithm. We'll see its classical and quantum solution. And then we'll spend time, significant time, in why it works, how it works, physically what all you do, mathematically what all you do with all those matrices, operations, all those kind of things. And then how do you make it work using in quantum circuits using quantum gates? We'll spend significant time, major part on that. Primarily, the message for today's session is that this new way of thinking, quantum superposition, all those type of things, it actually works. It works differently, but it works. Why I need to say this? Because you would have come across one common statement that all this superposition and so many, say, states are possible. That happens only while it is in superposition. Ultimately, when you measure, when things are of some value to you, it collapses into, say, one of the two definite classical states. So then what's the point? How do you use it? So that's what we are going to learn today, that it works. That even while the coin is flipping, it is in air, it is flipping, you can do things. And when it comes down and it lands head or tail, you get something out of that process which has happened earlier. Now, once you start feeling it, understanding is a different word. If you start feeling it, you get that feel that sometimes, in dream, you see something which is very realistic. But then when you get up, suppose you find that coin in your hand, something that you are seeing in the dream, and you are all of a sudden, you find something very weird has happened. What is it? I thought it was a dream, but then something is there in my hand. It's that much weird. It sounds that much weird. So that's what we are going to learn, that this new system of thinking, it works. It works. So we'll take one problem, we'll solve that problem using this DJ algorithm. And any matter that is related to understanding, this prime understanding, I will take it up, which means if there is a question asked in between, and I feel that if I do not answer this question, then your further understanding will be affected, I will take that question. I'll stop in between, I'll take that question. This session is targeted for beginners and especially at school level. So at certain points, you will see I have simplified certain things to the level of a school child. Say, for example, if I say 0 changes to 1, 1 changes to, say, and so don't get that feeling that now it is no more a normalized state. I will come and I'll settle that also. But I simplified it so that the basic message about the quantum way of solving problems, it works, that message goes through. So this will set up the content for this session. The contents primarily, we will state a problem and we will have an overview of the solution, the classical solution and the quantum solution. And then that dreadful word in academics, you will evaluate whether I'm able to communicate to you or not. Then we'll have a single qubit solution using the beam splitters which Jyoti ma'am covered in session 3. We'll revisit that Mach-Zehnder interferometer and all those matrices that other of my worthy colleagues have been taking from time to time, especially Vandana ma'am took it so beautifully on Monday, and then Kiran sir has been taking for the last 2 days. We'll see that all that superposition interference. Then we'll place a phase shifter in between and see. And believe me, I will make it simple. I have worked on that part, making it simple to the extent that a school child can understand. Don't worry about that part. That I will ensure that you find it easy. But then we'll have a quiz. And then we will see the typical DJ algorithm which is given in the books and how it is realized, say, it is made to work using quantum gates, circuit, and then we'll have a small quiz. And then we will have a little bit of homework. Homework will be primarily based on things which I leave out. Say, for example, if the derivation has 2 parts and similar part, and if I derive one part and I say similarly, and I use the result of the second part, I'll give that full derivation of the second part to you. So homework will be easy. Don't worry about that. And before we leave for our homes, we will have a final closing quiz, which you will have to submit for your certification. So algorithm, a word about algorithm, that it's a set of rules to be followed in calculations or problem solving operation. And in classical computers, it is executed using logic gates. I'm sure you can find better definitions of it on Google. Quantum algorithm should be something similar, but then it uses something which is essentially quantum in nature. And quantum in nature by mean superposition, entanglement, and the measurement which results in the collapse of the waveform. See, typically these 3 things are typically quantum. That superposition, entanglement, and the measurement which happens at the end, which collapses the wave function. Something typically quantum should be there, so you call it quantum algorithm. So in quantum computation, we primarily have some input qubits. Those qubits are acted upon by quantum gates in a quantum circuit, and it terminates with a measurement. With this, I come to the main part of my, say, we need a different problem today, which can be stated in a way that quantum phenomena can be applied. In this case, superposition or measurement. And we need to have a different set of problem. And remember, it's only in superposition that a qubit is different from bits. Otherwise, a qubit also has value 0 or 1 those definite classical states, it has 0 and 1. But then the amazing part of that qubit is it can have combinations of those 0 and 1s, so, and which happens in superposition. So the work should get over before that superposition state collapses. So with that, I come to the statement, the key problem of this session that we will solve using that DJ algorithm. So we have a single qubit. Single qubit means like you have one bit. The bit can have two values, 0 and 1. We have a single qubit and its definite classical states are 0 and 1. When it falls back to measurement, either 0 or 1. Now, some function acts on this qubit. Some function acts on. So this, because this qubit can have a value 0 or 1, so the function can leave 0 as such or change 0 to 1. Or it can do the other way around. Say it leaves 0 as such, F1 and F2 are doing it, or it changes 0 to 1, which F3 and F4 are doing it. Another possible state, another possible value for that qubit is 1. Now it can keep 1 as such, which F2 and F4 are keeping, or it can change 1 into 0, which F1 and F3 are keeping. So you see, there are only, for a single qubit, there are only 4 options that you can have functions of 4 types. One is this type. Say it leaves 0 as such and changes 1 also to 0, so that both the outputs are same, which is 0. This is one function that you can have. It leaves 0 as such, changes 1 also to 0, so the output is same and that same value is 0. Or it leaves 1 as such and changes 0 also into 1, so that the output is again the same, and that which is 1. This is one set of functions that we have. Another one, either it keeps 0 as such and 1 as such, or if it changes 0 to 1, then it also changes 1 into 0, so that you have a balanced output. You have equal number of zeros and ones. Equal number of zeros is applicable when you have more number of outputs. Equal number of 0 and 1, these are balanced functions. Now listen to it once again. A balanced function will give you half of the results will be 0, half of them will be 1. But a constant function will give same outputs, whether it is 0 or it is 1, the same output. So we have 2 types of functions: constant functions, balanced functions. The question for which we are seeking the answer today is, if you are given a function out of these 4, if you are given a function, is the given function constant or balanced? That's the question that we want to solve. Very simple, very basic, fundamental type of thing. But then you will be able to see quantum mechanics at work through this question. Now, note one thing. Before you start answering, note one thing. There is a superfluous knowledge that we don't need. The question is, out of these 4, which function is constant, which function is balanced? Now, these 2 are balanced. But then you see, there is an additional information. This is balanced because 0 was kept at 0 and 1 was kept as 1. This is also balanced. If it changed 0 to 1, it also changed 1 into 0. Now, this additional information, what the function did to 0 and what it did to 1, is not required. Do you see? The question is the function constant or balanced? Means, is it giving equal number of ones and zeros, or is it giving the same output? The question is this. But what we have the information in this table is what it did to 0 and what it did to 1. But I don't need that information. Now, what if you say, no, sir, you might not be needing that information, but I need it. In that case, you find another problem to solve. Then this is not the ideal problem to solve using DJ. So are you getting it? The problem we are restricting ourselves to is, out of these 4, you have to tell which function is constant, which function is constant, which function is balanced. Not what is it doing to 0 and what is it doing to 1. Is it balanced because of this? or is it balanced because of this? That's not being asked. Now, how do you solve it classically? The classical solution to this question is you give the input 0, find what is f of 0. Let's say that is A. You have made one measurement. Now give the input 1. Find what is f of 1. Let's say that is B. You have made this second measurement. And now you check, is A equal to B? That will define whether the function is constant or balanced. If A and B are equal, then it is a constant function. If A and B are not equal, then it is a balance. No, listen. How many measurements you made? You made 2 measurements to give this answer. What if instead of giving 0 or 1, we give the function a combination of 0 and 1? And you know what I'm talking about, you know, the superposition state. So the advantage that you have with a qubit, so say you have a single qubit and its state is given by this. Now, before I move further, let's check, is it even a valid state or not? So what is it? This is, you can write this as 1 upon root 2, this 0, 1 upon root 2, 1. If you square this, which comes along with state 0, if you square it, it gives the probability of this, say, particle, photon, whatever you have used, to be found in the state 0. So square it. What do you get? 1 by 2. Square this. What do you get? 1 by 2. The total should be 1. Yes, it's an acceptable state. It can be in this state. So if I give something like this to the function and I ask, what are you doing with it? Now, think of it. And if you don't understand, ask me, because this is crucial. When will this qubit not change? When will this qubit not change? Now, if f of 0 becomes 1, f of 1 becomes 0, you are again getting the same qubit. Or if 0 is left as such, 1 is left as such, again you are getting the same qubit. So your qubit is not changed if the function is a balanced function. But if 0 is kept as such and 1 is changed to 0, or 1 is kept as such and 0 is changed to 1, then you get same, then you don't get this qubit. The qubit has changed. So what is it which changes the qubit? The constant functions are changing the qubit and the balanced functions are not changing the qubit. So if you measure the state of the qubit, one measurement, you will get that answer. Instead of 2 steps, 2 measurements, you get that answer from 1. And that's what we are going to learn, say today, how to do it. Now we have covered up a little bit. I have spoken a little bit. I want to give you also a break from my voice. What we'll do is, just based on these things that we have introduced, we will have a short quiz, and so that I know that I'm able to communicate to you. So I'm posting in the chat, I'm posting this link. Kindly go to this, click on this link and answer those simple questions. And I will share with you the responses that we are getting. Once we get around, say, how many people are there? It shows 72, minus some people. So around, say, let's say. So even if we are crossing, say, 40, 45 people, I'll show you the answers. Kindly click on it. In the meantime, I'll see how many responses we are getting. Yeah. So it's a simple quiz. Acha, but purposefully, the quiz has been kept anonymous at this stage. The last quiz that you will take will have your name. But these quizzes which we take during the session, these are anonymous so that you feel free to try. You feel, you have the freedom to commit mistakes. That's okay. So we have got 1 response, 2. Okay, responses have started coming now. Good score so far. Okay, average score 4.25. 4. I got 9 responses so far. 10. We will look at the question-wise response once I cross this above 40 type. Okay, 24, 26, 27, Feel free to answer. Nobody knows what answer you have given, but you will know whether you are understanding it right or not. Okay, 30 responses so far. Around 70% people are scoring. Okay. See, someone has got 0 also. Doesn't matter. Nobody knows who has got 0. Nobody, including me, nobody knows. Feel free to commit mistakes. Okay. So we have crossed the halfway mark. And so now we'll go to question-wise response. Other people can keep responding, but then we'll move to question-wise response. The first one, the question number 1. Okay, let me take this summary from here. I'll take it from here. This one sounds a little bit better. So correct responses, 87% of the people gave correct response to the first one. Which of the following is a constant function? So around 88% people were able to identify the constant function correctly. Which of the following is a balanced function? Same 80%, 81% people were able to find which one is a balanced function. If you run the classical algorithm and see that f0 is 1, could you tell whether the function is constant or balanced? No, because f1 can be 0, can be 1, so it can give you constant or balance. You can't say. Just by knowing one value, you can't say. So there were more people committing error here. The superposition state of a qubit is given by this. A balanced function f acting upon it will change the state of the qubit. See, a balanced function, what it will do? Change 0 to 1 and 1 to 0. Or will keep 0 as such, 1 as such. So it will not change. So, but then a lot of people got stumped on this question. Okay, superposition state of a qubit is given by this. A constant function upon it will change the state of the qubit. What is constant function? It will either make both of them 0 or both of them 1. It will change the state. But then this is one question. These are the type of the questions that you found difficult to answer. So let me cover it up once again, briefly give you this thing. A balanced function will change 0 to 1 and 1 to 0. You again have the same qubit. Or it keeps 0 as such, 1 as such, you have the same qubit. A balanced function does not change the qubit. But a constant function will make either both of them 0 or both of them 1. So a constant function changes the qubit. And that's one measurement you have to make, that you have to just see whether the state of the qubit has changed or not. That's what you have to see, and you will be able to make out whether it's a constant function or not. So 50 responses we got, but there are 72 people in the group other than me. So there are 22 people who did not respond. Okay, no problem. Let's get back to the presentation. Okay, so let's move on to the second part now. We are revisiting that Mach-Zehnder interferometer which Jyoti ma'am presented on day 3. But today we are going to use more features of that Mach-Zehnder, and we need to understand it a little bit more deeply. So I'll share with you a few links for that Mach-Zehnder. Some of them have already been shared with you. All these links are little different in their own way. They are a little bit different. So first one, if you click this one, you click this one first. I'll take you through like how to use or what you are seeing there. So this is the first one that you will see. If you click the link that I have shared in the chat box, this is what you will see. Move to controls. Move to these controls. And this is what you will see. And click on the, I'll have to stop share because this, or what I'll do is I'll make this one little in so that otherwise I won't be able to. Just a second. Because those controls they get hidden under this. Yeah, now I can see these little more. Okay, now it makes my work a little easier. Okay, so this is the one that you will see in link 1. Now, right now, if you fire photon you can click on these things, show theoretical probabilities. So the photon will either be reflected or be transmitted. And this is that 50%, 50% beam splitter. So you have a chance of 50% here, 50% here. In terms of light, you say half of the intensity goes this side, transmitted, half of the intensity of light is reflected. In terms of photon, you have half probability of it being reflected, half of the probability that it is being transmitted. You get this 50%, 50%. Show quantum state. So this is the state that the photon was in when it was fired, when it was made incident on the beam splitter. And after it is fired, we'll come to this thing. This we'll come to this thing. And you can click on this, show matrix representations of optical elements. So there is one optical element here, the beam splitter, and the matrix related to this beam splitter is this. Here you can put some, someone is asking something. Okay, what you can do is you can put mirrors here. So just put mirrors, don't put the second beam splitter. Now with the mirrors, that this photon which it was going like this, or say in terms of light, if you say classical light, it was going, it gets reflected, and now instead of going here in this detector, it goes in this detector, and this one gets reflected, it goes into detector 1. But you see something here. See these two, let me remove the mirrors. This one and this one are more or less identical, they are similar. Only difference, right now the transmitted part was being detected by detector 1, the reflected part by D2. If you insert mirror, this transmitted part is detected by D2, this reflected part is detected by D1, but same 50%, 50% probability. You see something here, we'll talk about it. What is being done? If there is no beam splitter, only mirrors have been added, what has been done? We will come and we will discuss it back. We'll come back to this thing. You can insert the second beam splitter here. And this is something that was discussed in session 3. And now you have 100% probability of getting this D1 activated, and this D2 will not get any photon. Now I'm sharing with you the second link now. That has, there you can play around with phase shifters. So in the chat box, I'm sending you another link. Now click on this. This one is little different. Click on this control. This one, click on this control. And here you get this thing, insert phase shifters. This one is different because all these things are fixed. You can't change this, but you can only, the thing you can play around is you can insert phase shifters. Phase shifters are primarily glass slabs, and they make that wave to travel longer distances. And so the relative phase of these two paths, it changes. That's how it changes phase shifters. And here you have the option of inserting a phase shifter of pi, 2 pi, 3 pi, 4 pi. So visually they are showing it by a thicker slab, that kind of thing. I'm putting it back to pi and clicking on this thing, show theoretical probability. You know, it's coming because of the beam splitter and because of this phase shifter also. Now we'll discuss it more. Just understand the environment that we are going to talk about. Show quantum state, it will show the quantum state of the photon at various points. We will come to this also. What are all these things? And show matrix representations of optical elements. Click on all these things. So this is the beam splitter 1, matrix for that. Beam splitter 2, matrix for that. And this is the phase shifter, and this is the matrix for that. And we'll have a simplified version of this term also. Don't worry about that. So you have these two Mach-Zehnder interferometers, which we'll study. By the way, these are from QVIS, Quantum Visualization. This is this university. I'm sending you that link also. Because it's a, if you increase the number of system of beam splitters and mirrors n times, where n tends to infinity due to light, I want the probability for both the detectors be 0. Ultimately, it has to be at 1. It has to be ultimately, when you measure it, it has to be either 1 or 0. That's a one of the state. Now I'm sending you one more link. This is a link where all their simulations are kept. You can play around with as many of them, all free resources. Whatever you find convenient, comfortable. I have played with some of them. So these are the Mach-Zehnder interferometers that we are going to use. Now, please pick up paper, pen, and to motivate you that you write, I will write with you on the screen. So we start with this thing. Because you might have kept videos, these on your right side. So those who will watch the recording on YouTube, they will see some kind of blank here. But in Zoom live meeting, this part is covered by all those videos. So I have moved it a little bit left. So this superposition state, we will see how beam splitter say creates those superposition state in Mach-Zehnder interferometer. This is the apparatus. This apparatus looks very much like Michelson-Morley apparatus, which graduation and post-graduation students might be knowing. School students would have never heard about it. One of the most popular failed experiments. It wanted to detect that ether. The failure of that ether was revolutionary. That the experiment failed to detect ether, and they got Nobel Prize for failure to detect ether. One of the most popular failures. Sorry. So this is the apparatus. In that apparatus, one of the part is beam splitter. And the one we have been talking about, it has two beam splitters. One being used to create superposition, another for interference, that purpose. In quantum circuit, the same thing is done by Hadamard gate, and we'll see that also. And mathematically, you multiply by the matrix of this beam splitter and you get those superposition state. Don't worry, we will do it. We will actually do it. So let's start doing something, start writing something. We have this case of a beam splitter which reflects 50% of the light and which transmits 50% of the light. Listen to the case properly. Beam splitter reflecting 50%, transmitting 50%. Okay. If I call the transmitted part as state 0 and I call the reflected part as state 1, don't worry about it. It's actually, you can choose the other way around. That doesn't matter so much. At least for this session, it doesn't matter at all. If I call this state as 0 and this state as 1, and if both the paths are taken with 50% probability, what ensures this? This thing, half reflection, half transmission. In terms of photon, you will say there is a 50% probability of being reflected, 50% of it getting transmitted. How do you represent that state? 50-50 wala type. It goes to state 0, 50%. It goes to the reflected part, 50%. So how do you write that? Now the transmitted part I am writing as state 0. What is the probability? 50%. So what should come in front of it? The square of that thing, whatever you write here, the square of that thing should be 1 by 2. So what do you write here? 1 upon root 2. The square of it is 1 by 2. This is state 1. 50%. What do you write here? So what is the state of the photon after it has hit the beam splitter? The state is 1 upon root 2 and 1 upon root 2. I hope this part is, by now you are getting easy with it. So you can write the state of the photon after it has, say it has struck the beam splitter 1. You can write it even from your knowledge. Someone has responded in the chat. Okay. Okay, now this part, okay. This part is okay. Okay, now how do we get this? How do we get this? For that, we will have to go and study Mach-Zehnder a little bit more, and I'll start it in a general manner. Like this. Move it a little bit here so that I can see this end. Okay. Now it's okay. Now, if you feel that I got a ready-made thing here for me, I can start with a blank state also. I have kept one blank. I can use that. Let me motivate you by using something like this so that you don't feel I started with something on my plate. So very easy to make something look like a beam splitter. And right now, I need not worry about which side is dielectric, which side is glass. We will handle that. Don't worry about that part. whichever side. But then so the photon can strike it from above, the photon can strike it from below. It's my bad drawing. Photon will not have this kind of path. Better I correct my mistake before somebody gets this idea कि ये photon बड़ा नाश्ता आ रहा है. Okay, now say this photon coming from above, it can get reflected, it can be transmitted. Then you have those mirrors, easy to draw those mirrors. And then from here it reflects, and I'll talk about the second beam splitter later. We have a lot of things to learn before that also. Same thing can happen to this photon, which is from the lower left corner. A photon can come from this side also. It can get transmitted, it can get reflected within it. Now we saw this part, a photon coming, and we wrote that state. Now, and anything that you don't understand, ask me, because these are fundamental things, and I'm willing to spend more time to clarify. Say the state that a photon takes this upper path, the state that the photon takes upper path, if I write that with this, and what is it? You know, this is a zero state. And the state that the photon takes the lower path, if I write it with this, so what is it? This is 1, this is 0, this is 1. You know, if the photon was coming from here, and same thing I can write here also. If it takes the upper path, you write it like this here, you write it like this here, and you will see that in that Mach Zehnder which I shared with you, he has started with this thing. So if the photon is taking the lower path, you write 0, 1, 1, 0. If you start with this, just now you did that exercise. What will come here? This. What will come here? This. So what is the state of the photon at this, when it, say from left to right it is moving? When it has reached these things, this point, when it has reached this point, what is the state that the photon will be found in? 1 upon root 2, 1, 0 plus 0, 1. This is the state of the photon if it has crossed this one. Because it was having 50% possibility, and this state you were able to write even directly, even without any other help. But then on the left, the photon might have come from here, might have come from here. If it comes from here, you wrote this. If it comes from here and 50% reflection, and say reflection is 50%, transmission is 50%, these 1 by root 2, 1 by root 2 must remain. That's our common sense that we have developed now. If it is getting reflected 50%, transmitted, this should be 1 by root 2, 1 by root 2. But then there will be some phase difference. Why? This one, when it gets transmitted, there is no change of phase. But this one, when it gets reflected, this you might not be seeing. So this one, when it gets reflected, has a phase change of pi. And when it gets transmitted, it does not have any phase change. But then when the photon comes from above, then this one has a phase change of pi, and this one has no phase change. So when you wrote this photon after it has crossed beam splitter, and you wrote it like this, now when you write the state of this photon when it crosses this one, these parts should be the same, 1 by root 2, 1 by root 2, because the probability of being found on this path is 50%. Probability of being found on this path is also 50%. But it cannot be exactly the same because the phases are different. And now you will remember Vandana Luthra ma'am and her session on Monday, and I really like that session a lot. Now you will realize it, what was changing the phase, those beautiful, those arrows which were rotating all around the globe. Now you will start remembering it, that which gate does it in electronics, something. But yeah, I'll cover that. The problem is, what about left of this beam splitter? Here I know 1 by root 2, 1 by root 2, because whichever photon you take, it has 50-50 chance. This one is easy. What about this? If it is coming from here, then only this is there, this is not there. If it is coming from above, only this is there, this is not there. In general, what you do is you write this state as like this. Say if this has alpha here and beta here, if this photon has been fired, then beta square is 1. If this photon has been fired, then alpha square is 1 and beta is 0. Are you getting it? In general, it's written like this. Let me make this thing a little bit more clear. See, this alpha beta is the same as you write as it's the sum of this, which is the same as alpha multiplied by this and beta multiplied by this, which is the same as alpha 0 beta 1, and that's how we write those superposition states in general, alpha beta. So if you want to find the probability of being found in 0 state, is alpha square. Probability of being found in state 1, beta square, those kind of things. So this version allows you those matrix multiplication much faster. These are the states. We'll see the advantage of the various approaches. So we are writing this stage here. If this photon is being fired once again, beta square is 1, alpha is 0. If this photon is being fired, alpha square is 1, beta is 0. Now it comes to this point. Now what happens here? Till this point, am I okay? Till this point. Now, what has the beam splitter done? The first part, what has the beam splitter 1, what has it done? So let me change the color now. This is the beam splitter 1. The matrix for beam splitter 1 is 1 upon root 2 minus 1, 1, 1, 1. This is the matrix for beam splitter 1. This is the photon that we have taken, means beta square is equal to 1. Alpha square is equal to 0. This is the photon that we have started with. That's the Mach Zehnder I have shared with you, the link that I have shared. When this matrix acts upon this one, what do you get? You get 1 upon root 2. This is 0. This is 1. Now this is 0. This is 1, which can be written as 1 upon root 2, 1, 0 plus 0, 1. Which is 1 upon root 2, 0 and 1. So you see that the state which you were writing from your intuition, that's say 50-50%, that's what this beam splitter has done. It has created this state which we had already written here by saying 50%, 50% we had already written. This is what this beam splitter is doing. And mathematically, how you get this state? You write the matrix for this beam splitter. It operates on that state and it creates this space, which is your superposition state. So now when the photon has reached here after passing through beam splitter, this is what you are having. Now it strikes the mirror. Let's go back to the one that I shared with you. Is this the one? No. Oh. It is having so much of ego. Acha. So this is the one. Now let me remove the second beam splitter. Now, do you identify this thing? After mirrors have been put up, see, this is the state that you got from beam splitter 1. Now, after it strikes the mirror, do you recognize this gate from Monday's session? Acha, I think most of the people know. No, I'm looking for this answer. This is a very popular one. Are you able to recognize what is it doing? I teach some students JEE Mains previous year questions. And when I ask questions, this is a usual thing that happens. Okay. Oh, sorry, you are answering in the chat. Good, very nice. So yeah, that's very right. Very right. Now see what is happening. Now please understand it. See here what the mirrors have done. This one changes 0 to 1 and 1 to 0. This is your X gate, equivalent to the NOT. It changes 0 to 1, 1 to 0. Now this one was, remember this, what was it? Going back to this one, what was this state? 0. So it has changed 0 to 1, 1 to 0, but then this whole state doesn't changes. It has primarily flipped. It has primarily flipped those two rays. So what was going this side is actually, it comes here and it goes from here, it again goes to D1. That's where I was saying it is still in the same phase. That what, so these mirrors have flipped the beams. And say by change, this state is now, if I draw it here, if I write the same thing here, if I say what is the state, this has changed to 1 upon root 2, 0, 1. This has changed to 1 upon root 2, 1, 0. Yeah, overall state is still the same. That doesn't change. Now, when it comes to beam splitter 2, and we are very close to this discussion part, and then we'll put up this thing and we'll see how that DJ comes into picture. This beam splitter 2 has this matrix 1, 1, 1, minus 1. And what is the state here? What is the state here? How do you write this state? You write it like either like this or what? How do you write it? 1 upon root 2. The shorter version is this. Same thing like this one. This alpha beta you wrote like this. You write it like this. So give this state to beam splitter to work upon 1 upon root 2, 1, 1. And what do you get? You get 1 by 2. This is 1, 1. This is 2. And this is 1. This is minus 1. This is 0. And so you are getting 1, 0. So this Mach-Zehnder interferometer right now with no phase shift something, what is it doing is, if it goes in like this, out will come is 1, 0. This state will come out. Now, few questions that might come into your mind because they came into my mind also initially. Why to have all this kind of thing? Why not? I said, do you recognize this one? Beam splitter 2, do you recognize this gate? I remember ma'am talked about it. The popular one, anyone who remembers this gate? Some people are answering in the chat. Let me check. Yes, not X. H, Hadamard. Yeah. Okay. Thank you. Very right. No, so I thought, see, this, I said, why not? Because Hadamard gate creates superposition states. Why not put that Hadamard gate here also? Why to, bend and twist the things like this thing? And this is one of the things that I like to give it to you as a homework. I can put, why this? Okay. I can put this same matrix here also. I can try putting it here also. And then I put it again here also, again the same. What should I get? If this was 0, 1 here, you will get 0, 1 here also. I say, why not then talk straight away so that children can understand and I can understand. And it's very easy to say that you start with 0, 1 and nothing has happened. You are getting 0, 1 outside. No. The thing is, if you see how these Mach-Zehnder interferometer is actually made and how they are placed and how that physically it is working, you have to set things in a way and then you say this operation will be done if I modify this matrix in this way, that the first one will do this work and the second one will do this work. Okay, it will result in this thing, that 0, 1 will result into 1, 0. But okay, that's the state that I get when there is nothing in between. That if I start with 0, 1, it comes to 1, 0. Now, if I put a function which leaves it at 1, 0, then it must be a balanced function. But if it changes something like this thing, if it changes this 1, 0 to 0, 1, then it must be a constant function. And that's what we'll be looking for by putting. So these things I have covered up. These things I have covered up. Yes, these I have mirrors I have covered up. Now, if by putting the phase shifter, this is what we'll be doing, that how that output qubit, the state of the output qubit, if it is changed or if it is not changed, that's what we'll be looking at. So now what we are doing is, we are putting this phase shifter whose matrix is given by this. Now, those who are scared from complex numbers and all these things, I'll give you an easier version of this thing. Just a minute, let me change the color of the ink. I like red more. This thing which can scare some of us, e raised to the power, this is 1. I pi. Actually, it is how many pi? That I'll discuss later on. This you can write as cos pi plus I sine pi. Now sine pi is 0. So this thing is primarily minus 1. So this whole matrix you can write as 1, 0, 0, minus 1. This is what you can write it as. So this phase shifter has, to simplify things for you, not all, but this phase shifter has this as the matrix. Now, once again, this is the photon which is coming in. This is the one. And the state of this photon was 0, 1. Remember, it is coming from the lower path. This has beta, where beta square is equal to 1. This is the one. When you come here, the state of the photon, let me mark these points, A, B, and then you have these mirrors. These are the mirrors, M and M dash are the mirrors. At A, the state of the function is 1 upon root 2, 0, 1, 0, say 0, 1, 1, 0, whichever order, say, okay. This is the state here. Now, what happens? B does not get affected because there is nothing here. Nothing here. But this one and this one is what? This one is what? To be found in the lower state, 0, 1, 1 upon root 2. This is what is here. This one, when acted upon by this thing, let's do this operation. Let's work out on these two things. So this 1, 0, 0 minus 1 acts on 1 upon root 2, 0, 1. What do you get? What do you get? 1 upon root 2 is there already. 1 into 0, 0 into 1. So this is 0. 0 into 0, minus 1 into 1, minus 1. This is what you get here. Now, for the sake of simplicity, I am cancelling out the effect of these mirrors that we have already discussed. We have already talked about. I am cancelling out the effect. Say both of them, they create a phase difference of additional difference of pi. For the sake of simplicity, they have compensated. Or you can say this path is now starting from here. This path, say this path has gone here and this one has gone here. That's what we saw was the effect. That it basically interchanges that path. Now when you reach here, the 1 minus 1, the matrix for this, and the state that you have here, the state that you have here is this state as such, 1 upon root 2, 1, 0, and this one. So what is the state here? 1 upon root 2, 1, 0, minus 0, 1. Or in short, you can write 1 upon root 2, 1 minus 1. This is what you have, which will act, on which this beam splitter will act. So I'm writing it here now. 1 upon root 2, 1 upon root 2, 1 minus 1. And now what am I getting now? Before this beam splitter, I was getting something else. What am I getting now? I am getting now 1 into 1, 1, 1 minus 1. This is 0. 1 into 1, 1. And the minus is plus. So this is 2. And this one, this root 2 of this one, this also. So this is 1 upon 2. So this becomes 0, 1. If there is any part that I need to, now earlier I was getting here, what I was getting here, 1, 0. Now with this phase shifter being placed here, the qubit has changed. The qubit has changed. And if it has changed, I can make it out that what kind of function was there. Now I'm very much interested. I place it here. What about this? What about this? Because the function has to act on 0 and 1 both. So I'm little bit running out of time, but then what I can say, I can ask you to do is, the state of the photon is 1 upon root 2, 1, 0 here. Kindly pass it through this one and you will see it has no effect on 0. The 0 state remains 0 state. So I can put this here also. So F0, F1, both are being acted upon together. It does not affect F0. You try it out. So what I'll do is I'll change the color so that you know what is to be tried out. Color, बढ़िया सा color दो भाई हमारे को. Green, this green, let me see. So what you can do is, that this phase shifter 1 0 0 minus 1 acts upon 1 upon root 2 1 0, and you kindly check that there is no effect. No effect. So 0 remained unaffected, 1 was affected and changed to something, some phase change was there, and it resulted in the change of the qubit. It is able to catch that the function is of a particular kind. Yeah, that was a constant one. It leaves one, that 0 was left unaffected, and 1 was changed to 0, both values, and it has changed the value of this output, output qubit. Now, before I move further ahead, this is for practice, that's all homework type. Quickly, let's have a small quiz on this thing that we have covered so far. Quick, small, short quiz, so that I know that we are on the same page, we are understanding each other. There's a quiz that I have posted.
Tyagi sir, one submission, please.
Yes, sir. Please.
Please share the link in WhatsApp group. Some senior professors are also participating in the quizzes.
Okay. I'm so
possible
happy.
now. Otherwise,
yeah. Right now it is possible.
We can post after the program, after the session.
After the session, I can post it even now.
Okay.
Which one? Which group you are mentioning?
QC.
QC, there are 2 Qs. So there is QC1, C1. QC1, na?
Yes, sir. Yes.
Okay. So I am posting this latest one, I am posting it there. And I'll come back to sharing the screen so that I can share with you the response of the people. Okay, 4 responses I've already got. 5. Okay. The average score in 12 is 1.33 out of 3. So I hope you won't mind, because I tried it out with some, because I have access to school students, that this material takes little time to grasp. Yeah, see, the score has fallen down further now. Good. But yeah, keep responding, because your response gives me the feedback that the material has to be, softened even more so that everybody understands it. Oh, and in between, honestly, I was hurrying up thinking that, because, most of you are very good in this field, you're already good in this field. But yeah, I'll take time. So I'll request you to give me 5-10 minutes extra today. But then I won't like to hurry through this content. Okay, so we have more than 40 responses. So now let me go to question-wise response. Which of these will result a superposition state? Actually, all 4 will result in a superposition state. The last 2 would have confused you. And okay, I understand why you got confused. Because if you got confused with this, it means you haven't programmed with the text a matrix. So if you want to write like 1, 1, 1 minus 1. So you write 1, 1 like this, and you put a comma, and then you write 1 minus 1, the second row. Then you write the second row after the comma. So you see, this one is the BS1, beam splitter 1, and this is beam splitter 2. And both of them can create that superposition state at a time. Any one of it, if it is used, it can create a superposition state. Yeah, I understand why these 2 were confused. That was actually a good part of the question. If photon incident from lower left is being represented by 1, the matrix for beam splitter 1 is shown in the question. It will result in a superposition state given by most of the people, 2/3 of the people were able to answer it correctly. The matrix representation of a phase shifter is shown. Which of these is true? And we saw it, but then still half of the people got it right. That it affects the state 1, but leaves the state 0 unaffected. Yeah, because we did not work on 0, I just said that you try it out and you got a wrong answer there. See, now you do this thing yourself now. you have the matrix representation of the phase shifter. I'll go back to that part. You have the matrix representation of the phase shifter. This one, where is it going? This one. You have the matrix representation of the phase shifter. Let it act on this part, the photon, probability of photon to be found on this path. This path is this 1 upon root 2 1 0. This is what I started with. And that's why I was taking so much of time. Like, say, what is the how do you write if the photon is on this path? How do you write if the photon is taking this path? And if there is 50% probability, how do you write that? So this is that upper part, upper path. If the photon takes upper path, let this phase shifter act on it, and you will see there is no change. So it does not affect 0, it affects only 1, and that's why it was able to change the qubit. If it changes 1 to 0 and 0 to 1, then it's a balance function. In that case, it will not affect that qubit, and you will know. That's how you will know by single measurement that it's a balance function. Now let's move a little bit ahead. I think we saw all the 3 questions. We analyzed all the 3 questions. Okay, now moving ahead. Quantum algorithm, there are categories. You can find a better slide on the internet. This I won't spend time on. I'll spend time on something which we can do together. All these things, how you categorize quantum algorithms. We have taken just one quantum algorithm, and that also a very simple algorithm, so that we understand that how quantum mechanics work. But then when you start working in the field of quantum, say, computation, there are other algorithms that you should know. And this is the one that we are talking about today. In short, we are calling it DJ. And you know why we are calling it DJ? Because I have problem reading these names. Right from my childhood, I used to find how to read it. And I really wonder, like, how they get the name. But then, yeah, they must be thinking the same thing about our names, that how we get these names. Okay, now, the way DJ algorithm is put in books, and say books means using quantum gate in a quantum circuit, how do you visualize it? How do you realize it? Now, one thing additional that you will have to learn, this was covered by Kiran sir yesterday. He was covering it up. This sign, this plus in a circle, this is addition modulo 2. So addition modulo 2 means if these two things together are an even number, you keep that number. But if it becomes 2, you reset it to 0. So primarily the remainder after dividing by 2, that's what is addition modulo 2. To simplify it, if you get 0 or 2 or 4, the answer will be 0. But if you get 1, 3, 5, 7, etc. something, we will get only 1. Don't worry about it. If we get 1, you keep it as 1. If this is 1, and it is coming out to be 2, reset it back to 0. Okay. So that's what this modulo 2 means. In short, we call it mod 2. But this is addition modulo 2. Addition modulo 2. Now, this function fx, which you are trying to determine whether it is a constant function or is it a balance function, it is implemented by this, which sounds very similar to the C0 gate which Sir Kiran sir was sharing yesterday. There it was only x and y, and when you apply C0, x is the one which will determine, say, what happens to this one. Okay, I'll take that part later. X remains as such. And this y, there it was y addition modulo 2, say mod 2 x, y mod 2 x. Effectively, what C0 does is, if this is 0, then because x will be 0, so y is 1, so this term is 1. If y is 0, this is 0. If x is 1, then 1 plus 1 will become 0, 1 plus 0 will become 1. And so primarily, or say overall, what C0 gate does is, if this x is 0, it keeps y as such. But if x is 1, it flips y. That's what that gate was doing, and sir discussed it. Now, here, this is called F modulated or F controlled C0 gate. This F is controlling it. And the way this F function is implemented in these quantum circuits is by this argument, this one. Don't worry. If I ask a question in quiz based on it, I will give you this expression. You need not mug it up for today, but then you need to understand how it is being implemented. For example, if this x is 0, go back to that color which I like. I like that red color when I write. If this x is 0 and this y is 1, this is 0, so this will remain 0. Y1 modulo 2 of fx. And if fx, see x is 0, so you need to find out what is f of 0. What is f of 0? Now here he says if f of 0 is 1, then this 1 and this 1 will together become 0. And you will get the answer is this. Once again, you see it. Whenever I feel something should be understood, my simple way in my school, in my class is that I say, I'll ask it in the test. Then all of a sudden, most of the time students say, sir, what is the question? What are you trying to say? And it works. Somehow it works. So I'm telling you the same thing. I'm going to ask you in the quiz. If, say, how do you implement fx, this function? If you have x and y as 0, 1, just as an example, this is an example. If you have it 0, 1, you can have it 1, 1, 1, 0. So if you have 0, 1, this 0 remains as such. Y modulo 2 with fx. And if, say, this is also an example, just if f0 is 1, f0 can be 0 also. But you will see we'll generalize it, and we will get one result. So in between, mathematics will look frightening also. Don't worry, I'll bypass that. I'll bring you to the stage where you can understand get the meaning out of this algorithm. I'll bring you that. So this y is 1, f0 he says is 1, but then 1 and 1 modulo 2 when you say, because 1 plus 1 becomes 2 and 2 has to be reset to 0. So this, the answer will come out to be is 0, 0. So, and this is the circuit which implements it, that DJ algorithm. Now this gate, you know, H. So you know, instead of 0 and 1, what will be fed here? This 0 will become, by now you might have understood, that this 0 is mapped to this wala combination of 0 and 1. And this 1 is mapped to, this is spin right, and spin right. And this is 0 and 1, this one, spin left, right and left, that kind of thing. So this 0 is mapped to this combination, superposition of 0 and 1, superposition of 0 and 1. Both of them have probability 1 by 2, 1 by 2 type of thing, but then the phase is different. Spin right, spin left. So now what is being fed to this F are these two. And let me take you a little bit into that mathematics. If it is frightening, don't worry, I'll share this slide also with you. Now what you are having is this and this, because that Hadamard gate created the superposition of this bit and this qubit. And now I have color coded it so that you don't get lost into where we are. This 1 by root 2, 1 by root 2 here, which I have written here as 1 by 2, 0, and this whole thing plus 1 into whole of this thing. Okay. And now you have to apply this function. And we spend a minute or two to understand it. So let's see. Let's see now. How do you do it? How do you do it? So this is x, and this is now y. So x remain as such. These two together, I have written it here as 1 by 2. This is this 1 by 2. This x remains as such. And you see this x remains as such. And what is to be done with y? Y modulo mod 2 fx. Fx is what? F0. Y, this is y modulo 2 with f0. So you have 0 and f0 mod 2, z minus 1 and f0. So this and this goes here. This and this goes here. Are you getting it now? This one comes here, and likewise you are expanding this thing. This is a y. This is a y. So you get y first. You write y first. Write y first, and that modulo with f of, and this time x is 1. So this is f of 1. Why? Because x is 1 now. This time, this x is 1 now. This x is 1. This one, and you get this term. So what I'm Sheikh Talha. Don't do it. Okay. So this is what we have got on the previous page. Don't feel frightened. We did it ourselves. You can see it. I did it myself. Though I have made a lot of errors, But if you write it down, you can see that this can be easily done. Right? And I'm starting this page from here, and now I want you to understand something. F0 can be 0, F0 can be 1. This is something that you don't know. It is only in classical measurement you knew, but in quantum you don't know these two. You knew that is it constant or is it balanced, but you don't know what is F0 and what. But it can be 0, it can be 0, it can be 1. If it is 0, if F0 is 0, then this 0 and 0 is 0, and this 1 and 0 is 1. And so you get this part as 0 and minus 1. Likewise, if F0 is 1, if F0 is 1, then 0 and 1, this thing, 0 and F0, 1, minus 1 into 1. So this is minus 0 here. This becomes 0. This is minus 0. This is 0 and 1, 1. So I have rewritten it. This minus sign I have written first, and this is okay. I'll tell you why I'm doing it. This I can write as minus 1 raised to the power 1 of 0 minus 1. Can you see it? Because minus 1 I'm taking common. Here I can write minus 1 raised to the power 0, 0 minus 1. I have similar kind of thing. And what are these powers which are above? You see, these are the values of F0. So they can be written. We can combine all this thing together. For F0, we can combine it together, and it can be written like this: minus 1 raised to the power F0 of this thing. This is likewise. And you see, this is the homework. You try it out the same thing. If F1 is 0, if F1 is 0, then what you can write it as? If F1 is 1, then how you can write it at, and how you can combine these two. I'm writing the result here. This is something that I'll give you in the homework. And when you combine it, you get even more frightening kind of things. Yeah, when you look at it in first go, it looks frightening. But then you see this 0 minus 1, take 1 upon root 2 from here. This is that one state, original wala. Remove that. Whatever is left, you put a Hadamard gate on it. Where is that circuit? You put a Hadamard gate over it, and you put a Hadamard gate over it, implement this one, throw away this wala part, and then the second, but the remaining part you put a Hadamard gate, and what you get is something which looks frightening, but I can assure you, I'll discuss it with you, it is not at all. Let's see, let's discuss this thing. See, this is a qubit that you have to measure. Looks frightening, I'm telling you, but just give me a minute and I'll explain it to you. If F0 and F1 are same, if same means either both are 0 or both are 1. So you get, in both the cases, you get minus 1 raised to the power 0 or 2. In this case, this is 1. Are you getting this thing? This whole thing becomes, so 1 plus 1 is 2. 2 and 2 cancel out. So this state is 1 upon 2, 1 plus 1 of 0. So this cancels out. This is state 0 remains. If this is 1, this is 0, this minus 1 becomes 1, this cancels out. In the same situation, this one, this bracket has to be a bigger bracket. If F0 and F1 both are 0, minus 1 raised to the power 0 is 1. So this cancel out, this is 0. If these are 1 and 1, same, they have to be same. If they are same and this is 2, then again this becomes plus 1. So this is again 0. So 1 goes off and only 0 remains. So if Fx is constant, which means F0 and F1 are same, then this only 0 wala thing remains. The state reduces to 0. If Fx is balanced, then the state is reduced to 1. And by measuring only one qubit, you get, that's what Mach Zehnder, that detector measures. And by detecting just one qubit, you can tell whether it is a constant function or it is a balanced function. There is an activity, I'll give you the link. This is a beautiful site, this lab activity. I'll share it with you. And then we'll quickly go to a very short quiz, the third quiz. And I'll share, in the meantime, I'll share this one. But first you start trying this quiz. So chat. Chat, and here, this is the quiz. I'll stop sharing it and post it where Madhusudan sir asked me to post it. Yeah. Okay, so I posted it there also. And also let me get that virtual lab. You kindly try that quiz, and I will try this link. And I'll share it with you in the chat box first. Where's the chat box? Okay, here it is. Share the screen. Okay, this link I shared. Let's see how you are responding for the quiz. Oh, by the way, the second quiz got 77 responses. Now let's see how many responses we get in the third quiz. 19 already. And even the score is better this time. 22 responses so far. 23. Once we cross 40, we'll do that. Yeah, better score this time. Let me see what was the final score in quiz 2. 1.43. The first, and there were 77 responses. The first one got only 52 responses, and the average score, oh, that average score was good. It was 2/3, like 66, 67%. Okay, back to quiz 3. We have more than 40 responses. So now let me show you which quantum gate is used to create the superposition state. Most of the people know it. That because we were talking so much about C0, so people remembered the name. Okay, to determine whether a function is balanced or constant, classically you need minimum of A measurements, but with DJ algorithm you can do so with B measurements. A and B are quite a bit, but then okay, still more than 60% got it right. You need 2 measurements in this DJ algorithm. You need 2 measurements classically, but this DJ algorithm can get you done in 1. Classically 2, but DJ algorithm 1. Function fx is implemented as shown in the figure. If f0, this was the question we did in the class, and still 40% of the people, this is something that we need to enjoy. Yeah, quiz I told you this thing. This was a kind of the question where the teacher says on Monday we are going to have a surprise test, and still people are not prepared for that surprise test. That's okay. That's okay. We all are learning. Nobody knows what answer you are given. I told you they are kept anonymous for a purpose. So that brings me to the homework. Okay, listen. Homework. What is it? I said BS1 has one matrix, BS2 has another matrix. You put the same matrix BS2 wala, that Hadamard gate at 1 also, and try out the whole thing. And you put whatever you had at 1, you put it at 2. You will see it works. Theoretically, it works. Problem is in making an interferometer with those plates and putting it at what side do you put it up that you get this combination. Problem comes there. But as far as this session goes, it doesn't matter. So what you do is you try all those combinations. Other combinations that you can try is, we tried the photon coming from down. You try the photon from up. And that's where you start understanding that what is happening at what stage, what is happening at what stage. I am quite sure that the organizers will now make that group, say anybody can post and have discussions, because now those technical sessions are over. So that's discussion. People will like to have that discussion in that group. We will continue with that discussion there. With this, I thank you. And I really thank you, Kulkarni sir, for taking this initiative, for our president sir, for doing everything for this program to exist. Vandana ma'am, who has coordinated and done a lot of hard work, and especially thank you for all those sessions that I attended. I myself got a chance to learn. You can send me message anytime. You can be assured, I can assure you, I'll always reply to messages. This is the exit quiz, overall quiz, where your names will be collected. So this is the last thing that I'm sharing with you. This is that exit quiz. I'll post. Okay, I'll post you in that group also. With this, I hand over the mic back to Vandana ma'am and Madhusudan sir. Thank you so much. Thank you so much, everyone.
Thank you so much, Dr. Tyagi, for the wonderful insight and making this topic, which otherwise is not that simple, understandable at this level. And your insights about the balanced function and constant function and DJ algorithm, I would also call it as DJ algorithm. So in that was cleared by your in between quizzes also, and in order to simplify or in order to consolidate on the topic quizzes, intermediate quizzes, I think tells that how much audience or how much participants have understood, and that also helps in further flow of the lecture also. And I really like the way you reconsolidated on the gates and the beam splitter and Dr. Kiran's talk. So in a way, in nutshell, majority of the previous talks were also reconsolidated in terms of their understanding of the Pauli gates and Hadamard gate. And I'm very happy with the response of few people, Dr. Krishna Kumar, Yugen Kulkarni, then it is Pooja, Sauman Roy, Biju, Hemant, Baljeel, and then again Sauman Roy and Tara, Akansha, Atul. They have been constantly answering. And I'm sorry if I have missed few. I just noticed last two questions which you had asked about the gates. So that reconsolidation shows that how they are able to take an other aspect of it. Like in the previous case, we worked on the IBM composer, IBM quantum composer. So that representation was something different. We talked about probabilities, we talked about state vectors and the phases. And here you took an example from the beam splitter and with the help of the simulation. And in that, the perspective was different, but consolidating on the same thing. So that is
Yes.
the major important thing. And really thankful to you for that. And with that, I say this is the ninth session, and the enthusiasm of the participants is amazing because till now we have got around 72, and prior to that we had almost 90 participants every day, excluding 10 of us or 15 of us every day. 75 to 80 have attended, and they have participated in the quizzes also. So I think take home message is that interest in the sustained interest has been there. And I'm thankful to again Dr. Kulkarni, Professor Aluwalia, and all those who have taken part and have given us this opportunity, as well as have given the support also, all kinds of support. So thank you so much. And our team, that teamwork has been amazing, the way we have been, I'll say, listening and trying to make the things as simple as possible. Though things are very difficult to some extent, so nothing can be, I think, simpler than this. But still, we will always make an endeavor to make it more simpler. So I hand it over with my thanks. I hand it over to Dr. Madhusudan. Thank you so much, Dr. Tyagi. Thanks.
Thank you, Vandana ma'am. Before we conclude, I invite Professor Aluwale sir to intervene and give his remarks. Professor Aluwale sir.
Hello, very good evening. And I think it has been another wonderful program which has happened in the month of April and May. One thing which is very evident in this program is that if you have programs which are of interest to our community, they really accept these very enthusiastically. I will agree with Ma'am Vandana that the attendance was a very good indicator of the interest shown by the participants. But I think this is because of the hard work which has been put up by the resource persons. And it was not like this that we gathered from here and there the resource persons. They sat down, designed the program, and then came out with these series of presentations. There is one thing more which I believe the uh, teachers and the participants, student participants must have realized that the algebra of doing these transformations is very simple. It's not very difficult. But as we always say, uh, physics, when it comes in between, it really gives very interesting interpretations to the transformations uh, which happen. And that was evident in all the lectures which we heard. I'm really impressed by Dr. Rajiv Tyagi a lot. And the reason for that is that he's an enthusiastic teacher and loves to, convey what he has actually understood in a beautiful manner. Hats off to you, Dr. Rajiv Tyagi. I think
Thank you so much. Thank you
we
so much.
have found
Very
in you,
sweet compliment. Very sweet compliment, sir.
uh,
Thank you so much.
we have found in you another very competent member of the IAPT, and we look forward to very many future interactions uh, through you and through your school also, sir. Because now we don't only see you here, we also see your institution here, which has provided you space for being creative apart from your administrative duties also. So you are now our role model also. In fact, each of the speakers in this particular program were excellent. I can't emphasize more than this. And I know Vandana ji since my meeting in Goa, and we know that how she plans the things. We have together also done programs, and this is again another opportunity which was created by Vandana ji with the inspiration of our very young spirited Professor Kulkarni. I mean, he's an amazing person. He's an amazing motivator. He's very tough also. You must realize this. But I think his intentions are so good. That is what ultimately matters. And we are not going to stop here. I think we will continue with these things in future also. This is a series and it must continue. We should keep on evolving. And this is a kind of an evolution which is happening in IAPT these days. We are coming out with certain programs in which we are trying to be very, very self-reliant through the members of the IAPT itself. So this is a great time, great vision. And I missed actually 2 lectures in between because I was traveling all through. And I can see Kiranji's, I didn't met him or her, I don't know. And mm, Jyoti, she was just great. And the members who participated as resource persons in this, they are spread throughout the country. That is also one very good part of the presence of the IAPT in the country. So for me as president, it is very satisfying when our members come forward. I think they can do wonders. Tomorrow is the valedictory, and I hope I will be able to join, though I am traveling again tomorrow. But I would love to be there with you. And I will repeat my request once again. Vandana ji and Rajiv ji, Jyoti ji and Kiran ji, and Professor Kulkarni. I think it is high time that we convert these set of lectures into a small booklet by the name of this program itself, which was a wonderful name. I think it was very inviting name. Professor Abha is just great. I think she is proving the fact that she has the genes of Professor D.B. Khandelwal, the way she works. And every time she writes or intervenes anywhere, I think she is more in love of physics than with computer science. Fortunately, this program was a superposition of these two fields in a very interesting fashion. So thank you, Abhaji. Your Vidharva Sabharsi is also doing very well. It's very pleasing to note that. I must also thank today our beloved host, Madhusudanji and Professor Rao. They are very, very kind uh, persons, fully interested in the well-being of physics community and improving the quality of education. I think only one call was enough to bring them on the table and make these, not only this program, but an earlier program on quantum mechanics also happen. We must not also forget very many interesting things which are happening because of the participants. I have Dr. R. Balakrishna ji. Let me tell you that I have a very old, what you call, friendship with him. We were together in 80s, 1980s, in the last part of that decade in Jaipur. And we did a refresher course. And thank you, Professor Balakrishnan, for being with us in this program. This is just great. And then Dhwanil was a wonderful addition to take care of very many things which have happened. And Dhwanil, your presence also has lent a lot of what you can call strength to this particular program. And we feel that you will keep on joining us with the various other programs also. So once again, I thank each one of you. I may have missed somebody's name. Thank you, dear participants. You spent so much time with us wonderfully. There were so many quizzes which were given. It was a real, actually, I would call it as a truly a certificate program of 2 weeks, not less than that. It is in the spirit of what national education policy is talking these days. And if I look at the number of hours which have been spent, the number of hours spent are, including tomorrow, it will be 15 hours program. And 15 hours program actually is a 1 credit course, which is equivalent to a certificate course. So I'm doing all those calculations for you to tell you that how good you have been in participating in this particular program. So congratulations. Tomorrow, share your thoughts with us. And you are our thermometer also, which tells us that whether the things are properly cooking or not cooking, are we reaching the right kind of a temperature or not. Thank you, Vandana ji and Madhusudan ji and Professor Rao, Professor Kulkarni ji, Abha ji, Jyoti and Dhwanil and Professor Tyagi,
Reshma.
Reshma ji. Yeah, Reshma ji is also there in this program. Hello, Reshma. So that's
But she
wonderful.
has helped us enormously. And she has a team of volunteers also here. And I think we can't thank her enough for all the involvement and all the support she has provided.
Hello,
So
sir.
thank you so much to Dr. Reshma also.
Hello, sir. How
You
are
know,
you?
Ma'am Vandana, Reshma did a wonderful regional convention at Goa in which I participated. And
Yes.
I think we are finding some young now people who can really do wonders in IAPT. And they mean business. That's the best part of it. Reshma
Yes.
showed that it is fully evident in Goa itself. So thank you, Reshma,
Thank you, sir.
and well
Thank you,
done.
very- Thank you, sir.
Okay,
Yeah.
thanks.
Thank you, sir, for your encouragement for all of us in organizing these many programs. With these few words, I would like to sum up today's session. I thank today's speaker or today's what to call presenter, Dr. Rajiv Tyagi sir. Thank you, sir, for your wonderful and elaborative talk. And I also appreciate Dr. Vandana ma'am for holding this session in a skillful manner. I thank all the participants for their active engagement throughout the session. And this is goodbye for today. Tomorrow, we'll be having the last session and also the valedictory. So I think I request few participants to give their feedback during the valedictory session. The schedule of the valedictory will be posted in the WhatsApp group. Let us follow the schedule accordingly. I also request Halwale sir again to be there tomorrow during the valedictory session. With these few words, I'm ending the session here, and we'll meet tomorrow for the final session and also in the valedictory program tomorrow. Thank you, one and all. See you tomorrow.
Thank you. I'll try my level best. I am traveling, but still I'll try my level best.
Yes, sir. Please try to be there.
Okay. Thank you.
Thank you. Good night, all. See you tomorrow.